All right, let's dive in. Today, we're going to pull back the curtain on something that happens constantly, right inside your favorite gadgets. It's this invisible translation that makes our whole digital world, our music, our calls, our videos, all just work together. So let's see how it's done.
I mean, have you ever really stopped to think about it? You've got this huge, super high-quality audio file on your computer, but somehow it plays flawlessly through your tiny wireless earbuds? How in the world does that signal change size without turning into a garbled mess? Well, the answer is a really clever process called sampling rate conversion.
So the core of the issue here is what we can call the digital mismatch problem. Honestly, you can just think of it like a language barrier. Different devices speak digital at different speeds, and if they can't understand each other, you end up with errors and distortion and all sorts of nasty stuff.
That digital speed we're talking about, that's the sampling rate. It's just the number of times per second a device takes a little snapshot of a sound wave to turn it into ones and zeros. It's kind of like a camera's shutter speed, but for audio. A higher sampling rate means more snapshots per second, which gives you a much more detailed digital picture of the sound.
And this is where it gets really interesting. Take a look at this. A professional audio interface, something you'd find in a recording studio, might be capturing sound at a super high fidelity 96,000 samples a second. But your Bluetooth headset? It's probably designed to run at 48,000. So to play that audio, the signal has to be intelligently slowed down by exactly half, without, and this is the key, without losing its essential character.
So how do we actually slow a signal down? Well, the process is called decimation, and the best way to think about it is like shrinking a high-resolution photo. You can't just randomly delete pixels, right? You have to be smart about it if you want the smaller image to still look clear. But, as we're about to see, the most obvious way to do this has a major flaw.
Okay, so the simplest, most, let's call it naive, approach to decimation would be to just throw data away. I mean, if you need to cut the rate in half, why not just chuck every other sample? It's fast, it's easy, but oh boy, it leads to a huge problem.
And that problem has a name: aliasing. This is a really nasty form of digital distortion, where new, unwanted frequencies literally appear out of nowhere in your signal, frequencies that were not in the original recording. It's the audio version of a Moiré pattern, those weird wavy lines you see when you try to shrink a detailed image the wrong way. It just fundamentally corrupts the signal.
So here's the crucial takeaway. To do it right, you have to filter first. An ideal decimator uses something called a low-pass filter. Think of it like a bouncer for your audio. It only lets the low-frequency parts of the signal through, while blocking all the high-frequency stuff that causes all the trouble with aliasing. By getting rid of those problem frequencies before you discard any samples, you can shrink the signal down safely. It's like applying a slight, intelligent blur to a photo so that the final, smaller version is perfectly sharp and free of weird artifacts.
Okay, but what about the opposite problem? What if we need to speed a signal up? Say you want to play a standard audio file on a really high-end system. This process is called interpolation. And you can probably guess the analogy. It's like trying to enlarge a small digital photo.
Again, the simplest way to do this is something called upsampling. To double the rate, we can just insert a blank zero-value sample right in between each of our original data points. Presto, we've doubled the number of samples, so the rate is higher. But yeah, we've created a whole new issue.
This whole process creates these unwanted copies, or images, of the signal's frequency content up at higher frequencies. It's the digital equivalent of blowing up a small photo and just getting a blocky, pixelated mess. The information is technically there, I guess, but it sounds harsh and totally inaccurate. And wouldn't you know it, the filter comes to the rescue again. The ideal interpolator inserts those zeros, and then it immediately applies a filter. This filter's job is to intelligently fill in the blanks, basically. It smooths out all that blockiness and gets rid of those nasty spectral images to reconstruct a clean, accurate signal at the new higher sampling rate.
So we know how to double a rate, and we know how to cut it in half. But what about all the weird rates in between? Like going from a CD's 44,100 samples per second to the 48,000 used in digital video. For that, we get to combine both processes into one really elegant machine.
This right here is the universal solution. To convert a signal by any rational factor, let's just call it I over D, you do this three-step dance. First, you interpolate by I to get to some super high temporary rate. Then, you apply one single, masterful low-pass filter to clean everything up. And finally, you decimate by D to land perfectly at your target rate. It's just a beautiful, efficient system.
Now, you might be thinking, Wow, all this filtering and resampling sounds really expensive, like computationally. And you'd be right. If our phones and laptops had to do all these steps literally, our batteries would probably die in about 5 minutes. So engineers came up with a very, very clever trick to make it all practical.
And that trick is the polyphase filter. This is the real secret sauce. It's this sophisticated mathematical structure that totally rearranges the math of the problem. Instead of filtering a really long signal that's full of useless zeros, it breaks the filter itself into smaller pieces. And then it only applies the little bits of the filter that are needed to the actual non-zero data points. It completely skips doing any math on those useless zeros we inserted, which saves a massive amount of processing power. It's this elegant reshuffling of the problem that makes all this high-quality, real-time conversion possible on the devices we use every single day.
So the next time you stream a song or take a video call or watch a movie, you'll know about this silent, lightning-fast translator working behind the scenes. This constant dance of decimation, interpolation, and filtering is what lets all of our separate digital worlds speak the same language. The only question left is, just how many of these invisible conversions are happening all around you right this very second?